Okay, here we go with a proof of identity involving matrix transpose. So here's an identity to prove. Given any matrix A and any constant alpha, give an entry-by-entry proof that alpha AA transpose is symmetric. Right. First of all, I want to note something. This is not necessary for the problem, but I want you to note that I'm not assuming that A is square, but let's suppose A is n by k, then A transpose is k by n. So A transpose, if this is n by k, and this is k by n, the inner dimensions match, so the product is defined, and the result is an n by n matrix. So it's square. All right? So you know that symmetric only makes sense for square matrices. So in fact, A times A transpose will be a square matrix. That's not part of the proof. I'm just pointing that out so you can see that the problem does make sense. So let's just go to the proof using entry-by-entry format. Okay, let me scroll down. And I'm going to want to express alpha AA transpose I want to express alpha AA transpose in coordinate format. So if I want the alpha AA transpose ij, now what does the alpha do? The alpha just goes outside, right? That's by scalar multiplication. Okay. Right. So now what about AA transpose? This is ij. I need to use the matrix multiplication formula for that. If you go back to your matrix multiplication formula, what that looks like is alpha times the summation. Now here I have I and a j, so I'm going to need another index for summation. I'll call that k. And I'm just going to make the sum up to 1 to n. N is actually equal to the number of columns of A. But this is going to be A, ik, A transpose, kj. Okay, so that's summation formula. Okay, where do we go from here? A transpose kj is equal to A jk. So I can write that as alpha sum k equals 1 to n of A ik A jk. And that's from a definition of transpose. All right, well, let's not lose sight of what we're trying to prove. We're trying to prove that this matrix is symmetric. In other words, we're trying to prove that this entry ij is equal to the same matrix ji. And that will show that this matrix is symmetric. So let me go ahead and evaluate this same matrix with ji. Okay. So if I have alpha AA transpose ji, okay. Now I could go through the whole business again. However, this is just the same expression with j and I interchanged. Like I said, I could write every step down, but every step here will be identical to the step up here, except instead of ij, I'll have ji. So just go down here. So let me just go ahead and take the result and interchange j and I. So here you can see I is here, j is here. I'm just going to interchange those. Okay. So the result is equal to alpha sum k equals 1 to n. A jk a ik. Okay. All right, now, what's the comparison between this one and this one? Well, we know that matrices don't commute, but these aren't matrices. These are numbers. So in fact, aik, ajk is equal to ajk, aik. So I could write that down here as alpha sum k equal 1 to n of a ik ajk, and the justification for this is that numbers commute. Okay. Now this is just equal to this result here. So that's equal to alpha a transpose ij. And that's from above. Right? Since I showed that alpha a transpose ji equals alpha a transpose ij, this implies that alpha a transpose is symmetric. Okay, so I'll just reiterate that. It's not really necessary to reiterate that, but just to make it very clear what I'm doing. Alpha a transpose ij equals alpha a transpose ji for all I and j. That implies that alpha a transpose is symmetric. Now notice something. Here I asked for a coordinate proof, for entry by entry proof. Now you could do a simpler proof that's not entry by entry. That's not what I asked for, but let me just point out that you could do that. So here's a non-entry by entry proof. You could just take alpha a transpose. Well, let me not use square brackets, just use parentheses. Now, that's equal to, what does the constant do to it? The constant you can just take out because that doesn't affect the transpose. I mean, you're just multiplying the whole matrix by alpha. That's true whether you have the matrix or its transpose. So that's equal to alpha. So this is scalar multiplication. Okay, now what's AA transpose? Transpose. That's equal to alpha. Remember the formula. If you tap the product of two matrices and take the transpose, that's the same thing as the product of the transposes in reverse order. So it's going to be A transpose transpose times A transpose. Okay, and that's a transpose product formula. Okay. All right, now what's A transpose transpose? That's just equal to A. Okay, and so you can say since A transpose transpose is equal to A. Okay, so that means that since alpha A transpose transpose equals alpha A transpose implies alpha A transpose is symmetric by the definition of symmetric. Okay, so you see the steps. I give each step and I give a reason, and then using the definition of symmetric, that tells me that the matrix is in fact symmetric. So you should be comfortable both with this type of proof using the properties and the type of proof using the entry by entry method. Okay, so there are several proofs in the book that do entry by entry. I advise that you study those, and you'll see that those are quite similar to the procedure that I've done here. Okay.